Hey everybody, it's Ripley back again. We're going to talk about 8.5 power series. Now let's define a power series, and at first blush it's going to look a little intimidating, but it's really not that big of a deal, I promise. Alright, so we got ourselves a series. Let's, for lack of a better place, let's start it at 0. Who cares? We're going to go to infinity. Now all that a power series is, and this is crazy, it's a standard issue series. Notice that I'm changing my letter. Remember back when we did alternating series, we used lowercase b sub n. When we first started talking about series, we used a sub n's. Right? It's just a way of notating that this is the sequence which we grab values from to put into our series, to add them up. And then this is going to be times x sub n. Now, this is a little bit difficult to wrap our brains around. This works just like a function. Think of this not just as a series, but as a function. So the way this works is one, we pick a value of x in our brain. If you want to wrap your brain around this, say pick x. 2, plug it in, and then 3, make a series. Make a series. However, you can pick any value of x. It's x. You can pick negative 15. You can pick 27. You can pick 32. So instead of having one fixed value of x for which this series is created, it can be any value. Okay? Now, this one's going to make you a little bit crazy because it can either be written as c sub n times x to the n. That's kind of the base definition of a power series. But you can also write this as, man goes from 0 to infinity, of c sub n times x minus a. Now notice lowercase a, that's why we changed this guy to a c to the n. Now, we'll get into why this is in just a second. But what this is, literally is, a power series centered. It's centered, and I'll explain why that is in a bit, at x equals a. At x equals a. All right, now, for those of you that have had me for pre-calculus, for algebra 2, the idea of centering something at x equals a, like in this case, is kind of intuitive. It's kind of like if I were to take f of x equals x squared. We can all visualize that, right? This thing is driving me nuts today. However, what if I were to take, let's not do f of x because then I'm just committing all kinds of fallacies. Let's do g of x equals x minus a squared. See the difference? Remember, this is a parabola. It's centered, think about it that way, at the origin. This guy is centered at x equals a. The vertex is at a comma 0. Works the same way. You've got to think of power series not as being series, but as being functions. They work just like functions. Hand me an x, I'll hand you back a series instead of a y. Hand me an x, I'll hand you back a series. This guy just happens to be centered at a rather than at 0, which is where this guy's centered at. Now, let's play with power series for a sec. The best part of power series, the absolutely fantastic part of excuse me, power series, is to test for divergence or convergence. To test for divergence or convergence, you always, I don't know why I wrote you, always use the ratio test. In other words, there is only one test for convergence, ratio test, which is great. So if you identify a power series, you got to figure out whether or not the thing diverges or converges, it's a no-brainer. It's always ratio test. So, excuse me. So watch this. Let's take this guy. Let's go in, goes from 0 to infinity, and I'm going to go x to the n over n plus 1. Okay? Now, the difficulty of power series, that's supposed to be a 0. The difficulty of power series is unlike the regular old series where I can just kind of chug out the first few terms. Well, there's an uncountably infinite number of first few terms. You can give me any x, and I will make a series out of it, just like with a function. You can hand me any x, and I'll hand you a y back. But you're going to see something that's kind of fantastic with this, and I'll show you what happens here. Okay, first things first. We're going to go by the ratio test. Now just follow me along. You're on a little adventure here. You may not really know what's going on. So by ratio test. All right. I'm going to take the limit as n goes to infinity. Excuse me. God bless America. Of the absolute value of x to the n plus 1 over n plus 2, right? And then by the ratio test before, remember, we're dividing this. Does everybody see where I got the n plus 2 from? This is, you know what, I'm being a little lazy, or maybe I'm being a little too accelerated. Think of this as n plus 1 plus 1. Remember, the ratio test is the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. And then remember, if this is less than 1, I converge. If I'm greater than 1, I diverge. And if I'm equal to 1, do something else. Okay? Wow, that is just terrible. N plus 1 plus 1. And the absolute value, right? I'm driving myself crazy. This pen's making me nuts, guys. Sorry. And then I'll do it the long way the first time, and then I'm not going to do it anymore. So I'm going to divide by x to the n divided by n plus 1, right? And what this turns into is the limit as n goes to infinity of x to the n plus 1 divided by x to the n, right, times n plus 1 divided by n plus 2. Absolute value. All right? Easy, nothing to it, right? I just inverted, multiplied, and then used commutative properties of multiplication. So this turns into, now let's see what happens. This turns into the limit as n goes to infinity of, now watch this. What I have is x to the n plus 1 divided by x to the n. So I get the absolute value of x times n plus 1 over n plus 2. Now we're talking about n going to infinity here. N doesn't care about x. As far as n is concerned, x is a constant. So what I end up with is, think about it, as n goes to infinity, n plus 1 over n plus 2 just goes to 1, doesn't it? So this whole thing turns into the absolute value of x. Now you may be saying, wait a sec, Ripley, wait a sec, hold on, simmer down for just a sec. Why? This didn't equal 1, it wasn't greater than 1, and it wasn't equal to 1. So what do I do with this? Well, remember, the whole purpose of dealing with series is in the first place is to determine when they converge. I always want to determine when it converges. If it diverges, it blows up and goes to infinity, or it just flip-flops back and forth between values. It's not useful. It's not helpful. So what I do is I take this little piece of lovely joy and I say it's less than 1. Why do I say that it's less than 1? Well, because if the ratio test yields a value that is less than 1, I converge. So what this tells me is that the sum, notice this guy right here implies that x is between -1 and 1, right? Easy peasy, just definition of absolute value. So I know for sure that the sum as n goes from 0 to infinity of x to the n over n plus 1 converges if absolute x is less than 1. Now we're going to give this term a little lip service here in just a sec. There's a problem though. Remember, the ratio test was inconclusive if it equaled 1. So what I have to do is I have to check my endpoints. I check endpoints, because that's where it equaled 1 and the ratio test doesn't work. Okay? So I'm going to check my endpoints of this interval. My endpoints occur when x equals -1. All right, ready? So I've got the sum. I'm going to change colors here because this is really important. Students often forget to include their endpoints, to check their endpoints. So hopefully this will help you remember. Excuse me. So I get if x equals -1, then I have the sum as n goes from 0 to infinity of -1 to the n. Ooh, my spidey sense is tingling, divided by n plus 1. Does that converge or diverge? Well, the first thing you should notice is that this is an alternating series. It's a decreasing alternating series. Every subsequent term is less than the one before it. So it converges by a s t. All right, so what does that tell us? That tells us that any value between -1 inclusive and 1 converges. But let's test if I stick 1 in there. If I stick 1 in, I get n equals 0 to infinity of positive 1 divided by n plus 1. Oh, crud. Well, is that going to converge or diverge? Oh, wait, I can use my limit comparison test if I want to. That's always a good one. 1 over n plus 1 out at infinity behaves the exact same way as 1 over n. 1 over n is harmonic. Guess what? This diverges. And I would say diverges by, I'm going to use LCT. There are other ones that we can use if we had to. Right? So, what we have is, we have something called an interval of convergence and a radius of convergence. Now, this is a no-brainer, and we'll do a couple of problems here. I'm not just going to cast you to the wolves. This, excuse me, actually, I'm going to change colors. This guy right here is called the radius of convergence. And if you think about it, that makes sense. Radius of convergence. Now, why is it the radius of convergence? Because if you think about this, this power series is centered at 0. So on the real number line, this power series is centered at 0, and then I can go out to -1 and include it, or I can go out to +1 and exclude it. But the radius, the distance from the center of the series out to its edges, is 1. That's the radius of convergence. Now, I'm running out of room, so I'm going to have to come over here. Sorry about that, you guys. Let me change colors real quick, get back to black. So our sum was, what was it? It was as n goes from 0 to infinity of x to the n, damn it, over n plus 1. We know that the radius is equal to 1 because we knew that absolute x was less than 1. Okay? The interval, oh man, this thing's driving me nuts today. You know what? It's driving me so nuts, I'm going to write it on a smaller screen. Let's get rid of that. I'm going to write it here. This is making me crazy. Interval is think about it this way. Remember, it was included at -1. Included at -1 created a convergent series. At x equals +1, it produced a divergent series. So this is from -1 to 1. This is the radius. This is the interval. Isn't that fun? Now, how about this? Let's do another one. How about let's do find. The instructions are going to be find the radius and interval. Wow, it does so much more smoothly. And interval of convergence. Doesn't make my writing any better, does it? Of how's abouts, let's go the sum as n goes from 0 to infinity of, let's go 2/3 to the n times x minus 1 to the n. Okay? That guy right there. Now, think about what's going on here. This is a function. You hand me an x. Instead of handing you back a value, I hand you back a series. It's still a function. It's just a function whose range is a series instead of a number. I know, it's crazy. Trust me, before you're said and done with mathematics, everything's said and done with mathematics, you're going to have crazy functions that don't just hand you values back. They're going to hand you back all kinds of crazy things. Okay, so we're off to the races. We'll do this by the ratio test. That's the coolest thing about power series, is they're always determined by the ratio test. Nothing else. It's the only test that works. Ideal limit as n goes to infinity of the absolute value. Now I'm gonna start beating on you guys a little bit. Let's go to the n times n plus 1, sorry, times x minus 1 to the n plus 1, right? And then I'm going to divide that by 2/3 to the n times x minus 1 to the n.